All right, in this video, we're going to be looking at the two basic rules of probability. The first rule is called the multiplication rule. It's the most common probability rule we will run across. And it's to calculate the probability of two events happening. And to do this, what we're going to be doing is thinking about whether our events are dependent on each other, then we're going to use the top one, or if they're independent to each other. Let's start with the latter, the independent one. So flipping a coin and rolling a die. So suppose we want heads and a 1 on our die. So to calculate this, obviously these are independent events because we know that the coin and the die have no impact on each other. So what we do is we take the probability of the first one. So the probability of getting a heads would be what? 1 out of 2, 1/2. And the probability of getting a 1 on a 6-sided die would be 1/6. So we just take 1/2 multiplied by 1/6. And we can do this for multiple events stacked together. We just need them all to multiply together. And we calculate the probability of each, multiply them, and we get the probability that they all occur at the same time. It gets a little more difficult, though, when we have dependent events. So to find the probability of A and B, given dependent events, we want to find the probability of A. Then we multiply that by the probability of B occurring given event A occurred, because we need event A to occur in order for this to also happen. And event A impacts the probability of event B. So that's where the dependent part comes into play. A good example of that is this example. So here we have our rule of multiplication. So we have an urn with 6 red marbles and 4 black ones. 2 marbles are drawn without replacement. Whenever you see the words without replacement, you need to think that it's a dependent situation. If it was with replacement, that would be independent. What is the probability that both marbles are black? So A is the event the first marble is black. B, the event that the second marble is black. And then we calculate the following here. So in the beginning, there are 10 marbles, 4 are black. So the probability of the first draw is 4 out of 10 to be black. And after the first selection, now things have changed because we've set that marble off to the side. There are 9 left, and 3 of them are black because we need the first one to be black as well. So there's 9 left, 3 are black. So therefore, the probability that the second draw is black, given the first occurred, is 3/9. Then we take these probabilities, 4/10 and 3/9, we multiply them together, and we get our final answer. They just simplify that down. So that kind of explains how the formulas work, the dependent one and the independent one. And we'll go through some more examples on that, but let's look at the next rule. So the addition rule. This one is different because our first problem was asking if it's A and B, but this is going to be A or B. And this U stands for union, stands for or. So to find the probability of A or B, what we're going to do is calculate the probability of A plus the probability of B, and then we subtract where they meet in the middle. Let me go back to our Venn diagram. So think about our Venn diagram from a few lessons ago. Here's A, here's B. So if we add up everything in A, everything in B, we're going to count this middle part twice. So what we need to do is subtract that middle part, and that is what this formula is doing. It subtracts that middle part. And we also know if they're mutually exclusive, so those Venn diagrams are separate circles, then the intersection would be 0. And the union of these, so A or B, that's when you can just add them together because they don't share anything in common. All right, let's look over some examples. This person, Juan's trying to figure out where to go on vacation, New Zealand or Alaska. You can only afford one vacation. Probability chooses A is 0.6. Probability chooses B is 0.35. And we note that the probability of A and B is 0 because this person can only afford to take one vacation. So to calculate the probability of A or B, so New Zealand or Alaska, we take those probabilities, we add them together, and there is no intersection. So this person has a 95% chance to go on a vacation. The probability they don't go on vacation would be 1 minus that 95%. So a 5% chance they don't go on a vacation. and 95% chance they do. All right, so next is in the library. B, student checks out a book. D, checks out a DVD. So a book, probability of a book checkout is 0.4, 40%. DVD, slightly less, 0.3. Over here, they already had calculated the probability of a DVD given a book. So all the people that check out books that are going to check out a DVD, it's 0.5, 50%. So that's a pretty considerable or decently large amount, since we have only 30% normally checking out a DVD. But of these people, of the book people, half of them are checking out a DVD also. So the book has an impact on the DVD, since these two are different probabilities. So these are dependent events. So we want to find the probability of B and D. So to find the probability of B and D, we use our formula that was given. These are dependent events because these are, the book obviously changes the probabilities for checking out a DVD. If this was 0.3 and 0.3, then they would be independent. So the probability of a book and a DVD. So we calculate the probability of a book, 0.4. Then we calculate the probability of a DVD given the book happens. So that's 0.5. Then we multiply those together to get 0.2. So 20% of the time, a book and a DVD. So that's 20% of the overall. Even though we have 50% of the book people getting DVDs, there are still some people that get nothing. So we have to count those people into play as well. How about a book or a DVD? So for that, we're going to take the probability of a book, probability of a DVD, and then we subtract all the people that get both. So 40%, 30%, then we subtract the 20% that get both, and we end up with the 50% of the people that get a book or a DVD. All right, our next example is kind of a long one, but this is our last example for this. So studies show that one woman in about 7 who lived to be 90 develop breast cancer. Suppose that those women who develop breast cancer, a test is negative 2% of the time. So even though they get it, they still test negative. So that would be a false negative. We're kind of hearing about some of that with COVID. Also, suppose in the general population of women, the test for breast cancer is negative 85% of the time. So let B be a woman developing breast cancer, and N be a negative test. Suppose one woman is selected at random. So what's the probability a woman develops breast cancer? Well, they give that to us, 14.3%. So that's changing that to a decimal, 0.143. And what's the probability that a woman tests negative? So this is just a woman in general. So women are testing negative 85% of the time, so 0.85. Given that the woman has breast cancer, what's the probability she tests negative? And so that's asking us for this. Just looking at the breast cancer people, what's the probability they get negative? They get a negative test, 0.02, that's 2%. What's the probability that the woman has breast cancer and tests negative? Let's see, how is that different from this top one? Given that the woman has breast cancer, what's the probability? Okay, this one's asking for what's the probability? This should say, what's the probability that a woman has breast cancer and tests negative? So what we need to do is calculate the probability a woman gets breast cancer. And then we need to find the probability that they test negative given that they have breast cancer. So this is going to be very hard to have happen because we need to have breast cancer and test negative. Okay. So for this, we're going to calculate the probability that we get breast cancer, so 0.143. And then we're going to find the probability that not only do we have breast cancer, but we are also testing negative. So we use this answer from up above. Probability of cancer the probability of a negative test given cancer, that's 0.02. We multiply those two together. So a very small chance that this would happen. What's the probability that the woman has breast cancer or tests negative? So for this one, it's going to be pretty broad because it's just breast cancer or a negative test. So we take breast cancer, the negative test, Then we're going to subtract that small group in the middle, the people that have breast cancer plus the negative test. So here's the probability of cancer. Here's the chance for just the random negative test. And then we subtract that small amount in the middle. So there we go. About 99% of the people will either have breast cancer or get a negative test, which makes sense. You kind of either have it or you don't. Let's see. Are having breast cancer and testing negative independent events? And yes, the answer is no, because the probability of testing negative would be 0.85 or 85%. But the probability of testing no once you get breast cancer is 2%. So those probabilities are not the same. In fact, they're not close at all. So since they're not close, they're not independent, which makes sense. You know, if you get cancer, you're going to most likely test for it. Okay, are having cancer and testing negative mutually exclusive? So that would mean having cancer and testing negative, that means they would never happen at the same time. And we wish that was the case, but it is not the case. There is a small chance you will get cancer and test negative and not be diagnosed correctly. So no, they're not mutually exclusive, unfortunately. So yeah, the intersection must be 0. All right, so that's probabilities involving the addition rule, where we add these probabilities together and subtract the part in the middle. And we also talked about the multiplication rule when we have independent events down here. You can multiply those probabilities together, or dependent events. And you multiply the probabilities together, but it's a little more lengthy. So, all right, that's it for now.